continuing on with week 4 after we've covered the idea of linear independence, the beginning of the idea of bases and dimension and vector spaces and how these all go together. Now we want to say what happens if we change the bases. So week 4.2 is the context of change of basis. So this topic in general means that, like we discussed earlier, every single vector space that we have has infinitely many bases. So again, for a vector space to have a basis, it has to be, the components have to be linearly independent and they have to span the vector space. They span the vector space and they have to be the right dimension. So every vector space has a predetermined dimension. So every single vector space has the same amount of elements in every single basis it has. For R3, there's always 3 things in there. For our 2x2, there's 4 things in there. The things can look different, they can change, but there's always going to be 4 things and they're always going to be able to make that space. So with this idea, we need to come up with the idea of how can we change between these bases. So they're all valid, they all generate the same space. How are they related? So every vector in a vector space is represented by, so this concept I think doesn't get emphasized enough this class, which honestly would clarify a lot that I think helps if we talk about it a bit. So we just talked about the idea of why there's infinitely many bases and we want to change between them. So the second bullet point here says that every vector in a vector space is represented by the coefficients used to generate that vector using its basis elements. What does that even mean? So when we think about something that is a vector in R3 with respect to the standard basis, so let's say it's like 5, 2, -6. This is a vector in R3. That 5, 2, -6 is with respect to the standard basis if we don't specify otherwise. So what that means is we linearly combine the basis elements like this to get, oh, no, that's a 0, 5, 2, -6. So these numbers mean, okay, I did 5 times the first basis element, 2 times the second basis element, and -6 times the third basis element. That's with respect to the standard basis, so it's kind of implicit. You're like, well, obviously, 5, 2, -6 is a linear combination of 5 times 1, 0, 0, plus 2 times, oh, this is wrong. Wow, can't write at all. 2 times 0, 1, 0, and then -6, 0, 0, 1. Like, that makes sense, but we don't really talk about it because we usually talk about the standard basis. But here with 4.2, we're introducing the idea of different bases. So we need to explain this with reference to different bases. So every vector you've seen, if it's not specified otherwise, is with respect to the standard basis. So this subscript of this S tells us that it's with respect to the standard basis, so it's going to be linearly combined with the standard basis. When we have different bases, we'll have different subscripts here. It'll tell us, okay, now we're using a different basis, and this is the coefficients used from that basis. That's kind of a clarifying thing here. When we change between bases, we can multiply a vector that is in one basis by a change of basis matrix. So a matrix which we usually denote as a P, we call change of basis matrices capital P's, and we can change it to another basis. So looking at this computation, and let's imagine R3 again, we can take something that's in R3 with respect to the standard basis, so something like 5, 2, -6, multiply it by my change of basis matrix that goes from S to B. This is going to be a 3x3. And then we will get the vector with respect to the B basis. This is going to be a 3x1. So it changes between them. So the change of basis matrix changes between the bases. If you can imagine, the change of basis matrix is directional, right? This matrix, whatever it is, it goes from S to B. It does not go from B to S. It goes from S to B. So you take a vector that is in S, you multiply it by that matrix on the left, and you get the resultant matrix, the resultant vector. However, let's say you need to go the other way. If I want to get something from B to S, I can take that change of basis matrix and take the inverse of it. The inverse of a change of basis matrix will invert the order. So if I wanted to go from, if I had a change of basis matrix that goes from B to S, if I take the inverse of it, I'm going to get the change of basis matrix that goes from S to B. So inverting these matrices will get us to change the order. We can also squish together change of basis matrices to move between multiple bases. So looking at this expression here, I can go from S to B, and this is a matrix. Then I can go from B to C, some other basis. This is another matrix. And together, these matrices multiplied together will give me the change of basis matrix that goes from S to C, because the beginning here is S, the result here is C. And as you can see in here, that B is kind of being squished together in the middle. So you can imagine you have to put your change of basis matrices in the correct order that squishes the thing that you're not interested in the middle. That's the idea of change of basis. We're going to do a bunch of examples, so just if you can understand that conceptually, that'll help. The other topic that is associated with 4.2 is rank and nullity. All of these things kind of need to be defined. So I feel like I've alluded to them a little bit, and your class might have alluded to this a little bit before we got to this point, but this is where we formally define what all of these things are. So the row space, column space, and null space are all vector spaces that are associated with a vector. Associated with a matrix. The row space is the vector space that is generated by the rows of a matrix. So when you have a matrix, you have the rows. You can say, what if I linearly combine all of these rows in a certain way, I can make a space. This must be the rows in the reduced row echelon form. So given a matrix, you have to do the reduced row echelon form, and then you take the rows that are non-zero, the ones with those pivot variables, the ones with the ones, and that is our new basis. That is the basis for the row space. The dimension, so the number of things in the row space's basis, is the rank. So, which makes sense. Rank, when we've talked about before, is the number of non-zero rows, number of pivot variables. So rank is the dimension of the row space. Column space is very similar, but it's with the columns of a matrix. So the vector space that's generated by the columns of a matrix. Quick note is to find the basis for the column space, you have to do the reduced echelon form, figure out what your pivot variables are, and then you take the columns associated with those pivot variables. You can't just take you can't take those columns. You have to then go look at what variables those correspond to in the original matrix. You can't take the reduced row echelon form columns, because when we do these row operations, we do not preserve the linearity between the columns. We're doing row operations. The columns, this relationship between the columns can change. So we can't take the reduced row echelon form columns. We have to figure out which ones are our pivot variables. So those tell us which columns are important, but then we have to take the original columns from the matrix. The dimension of the column space is also the rank. It makes sense because for every pivot variable, there's a row for that pivot variable and there's a column for that pivot variable. So for every thing that's in the rank for the row space, there's going to be something in the column space. The column space can also be called the image of the matrix. What else? I feel like there's another name I'm missing. Yeah. So there's multiple words for the column space. The range. That's what I'm thinking of. Those all mean the same thing. The null space is something we've talked about a bunch already. So we talked about the null space, the kernel homogeneous solution. It's a vector space, and it's generated by all the vectors that set this expression ax equal to 0. So all of the x's that make this true. We've practiced this before. We solve the system ax equals 0 as described in 2, and then we can make those things that the column vectors that we are find, which are associated with the free variables. Remember, so these two things are associated with the pivot variables, and then the null space associated with the free variables. The dimension of the null space is called the nullity. So the nullity tells us how many things are in the basis of the null space, how many free variables you have. This kind of all comes together in something called the rank nullity theorem, which is a really important result in this class in math that tells us how the rank and the nullity of a matrix is related. So in this case, just by reading the definition, the number of pivot variables in the reduced row echelon form of the matrix corresponds to the rank of that matrix. And then the number of free variables in the reduced row echelon form corresponds to the nullity. So the rank is equal to the number of pivot variables, right? Pivot variables. And then the nullity is the number of free variables, which equals to the number of columns, which is also, we know, is equal to the number of variables. So that just like makes sense, but kind of relating pivot to rank and free variable to nullity is going to help you a lot in this class. So Whenever you're solving for a matrix and you're like, okay, I know the rank, what's the nullity? You can always just do number of columns minus rank, or the other way around. If I'm like, I have the nullity, what's the rank? It's always the number of columns minus the nullity. So, useful equation. Not too much to talk about it besides that it exists, and that you'll use it in the future. Okay, let's do some change of basis examples. So, let the basis b be this, and the basis b prime be this. So it's just two bases for R2, right? That's all you need for a basis for R2 is you need two 2x1 linearly independent vectors. Looking at both of those, they're two 2x1 linearly independent vectors. For R2, it's very obvious when something's a basis because it's pretty easy to tell when two things are not linear combinations of each other. Like looking at these two, I'm like, yeah, obviously I can't multiply this by something to get this or multiply something by this to get this. So R2 makes it pretty straightforward. And so let B is this, and where they're both relative to the standard basis, which we all know and love, which is just 1, 0, 0, 1. They want us to find the change of basis matrix that goes from B to B prime. So let's talk about first what information we have. So every time that you're given a basis, you are given a change of basis matrix associated with it. So for B, we have a change of basis matrix by putting our basis elements column-wise, and it always goes back to the standard basis. So in this case, this is the change of basis matrix B to S. That's just how it is. It's always like this, because you can always use this to go from something that's in with reference to B to something with reference to S. Same thing here, I can go from B prime to S using 1, 3, 1, 4. Trivially, we also can say S to S is just 1, 0, 0, 1. True. Everything always is just going to S. If you remember that, you're gonna be in good shape. They want us to find P going from B to B prime. So I want to find a way to put some of these matrices together so that I can form B going to B prime. In my head, okay, I'm starting something over here. I need to get to B prime from over here, and I'm starting from B over here. I have this guy. I can go from B to S, right? I am given that already. And then I need to get to B prime somehow. I can use S as a middleman. Go from S to B prime because those things are together here. It's being squished together in here. That's good because then it just only results in this solving for going from B to B prime. I have one of these already. I have the change of basis matrix that goes from B to S, and that's just 2, 3, 1, -1. I need the change of basis matrix that goes from S to B prime. However, I have the one that goes from B prime to S. To get this, I can take the inverse of this matrix and then I will switch the order. So then I can solve for B prime, S to B prime by taking the inverse of this matrix, which would just be going 4 - 3, and then switching the 1 in D, A and D, and then negating -1, -3, which then will give us 4, -1, -3, 1. That is my S to B prime. I'm gonna plug that in here. 4, 3, -3, -1, 1. And I now can just solve for what B to B prime is by doing this matrix multiplication. Okay. I will do it out. So it's always row times column. Row times column. This arrow. Times column. Second row times first column. Second row times second column. This gives me 8 - 3 is 5. 4 + 1 is 5. -6 + 3 is -3. And -3 - 1 is -4. And that's it. That is my change of basis matrix that goes from B to B prime. And that's it. So very simple first question. So now I could use this change of basis matrix to take any input vector v that's with respect to b, and then I will get something with respect to b prime, some vector, the same vector with respect to b prime. Okay, let's do another example. This one's a little bit more complicated. So we're given b1, b2, our two bases for R2. As you can see, they love to do examples with R2 for change of basis. You are told the matrix representation of a linear transformation. Okay, so this is getting a little bit ahead of ourselves. Linear transformations is 5.1, but just hold on with me here and understand that a linear transformation just changes a vector. So for our intents and purposes, all we're doing is a transformation. It's just changing a vector. But they're telling us that the input is with respect to b1, the basis b1, and the output is with respect to b2. That's what source and target mean. And look at that. What is the linear transformation M, where we have two different bases? So our input, we want it to be instead c1 with respect to c1, and the output is with respect to c2. So as you can imagine, we have to change the basis that the input is with respect to and change the basis for which the output is with respect to. So again, let's write out everything we know. So we have the change of basis matrix that goes from B1 to S, 1, 1, 1, 2. We have the change of basis matrix that goes from B2 to S, 2, 1, 1, 1. We have the change of basis matrix that goes from C1 to S, 1, 2, 1, 1. We have the change of basis matrix that goes from C2 to S. Oh, I forgot how to write a bracket. 1, 1, 2, 1. And then we have this linear transformation, MB2, so going from B1 to B2. And instead, we want it to go from C1 to C2. Okay. The way that I think this problem makes the most sense is I've got C2, C1. This is the same notation as if it looked like this. Those are interchangeable. It's just like this is the input and this is the output. So I've got C1 and C2. And in the middle over here, I have it going from B1 to B2. So I know that I need to change something that's happening on the output side. I know I need to change something that's happening on the input side. So I can use all of my change of basis matrices to, I know that I need something to be B1 here. I know I need something to be B2 here. I know I want it to end up being C2 over here. I know I want to start with C1. So I'm trying to just think, how can I squish all these things together to make this happen? Okay, I have every matrix I need, technically. I'll have to solve for some inverses, but I have them. So here, I can just go, using the standard basis is very helpful. Boom, B2 to S, and then S to C2. So as you can see, I have my results. So my C2 is going to be the output basis, and then my C1 is going to be my input basis. Then I've got the standard basis being squished together in each of these change of basis matrices. And then I have my B2 is with my B2, and then my B1 is with my B1. So this is my linear transformation, my M. So I need something on the right-hand side to be with respect to B1, and then I need something on the left-hand side to be with respect to B2 because it's input to the output. So that's why I'm putting this in this particular order. From the information provided, I have all of these things, right? So the ones I definitely have are everything going to S. So B2 to S, I have 2, 1, 1, 1. I have the linear transformation matrix. I have C1 to S, 1, 2, 1, 1. And then for these guys, I have to take the inverse of them. So going from S to C2 instead of C2 to S, I'll have to take the inverse of this. And then going from S to B1 instead of B1 to S, I'll have to take the inverse of this. So doing all of this matrix multiplication behind the scenes, again, I really recommend practicing this to practice your matrix multiplication, but it's a bit of a waste of time for us right now. I can do all this computation, blah, 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 and then I will get my matrix C2, C1, C1 to C2, so the same linear transformation, but with respect to two different bases, and I get that to be 4, 3, 2, 1. And that's my answer. second part of the question is B3 is another basis of R2, where we have the linear transformation going from B1 to B3 look like this. How is it related to B2? What is the change of basis matrix between B2 and B3? So this one's kind of just like showing us how to use this information a different way. So I have the linear transformation going from B3 to B1, is 5, 3, 1, 1. They want us to figure out what is the change of basis matrix that goes from B2 to B3. We already have the change of the linear transformation matrix that goes from with respect to B1 to B2, which is 1, 2, 3, 4. So the way that we can solve for this guy is using these two pieces of information, right? So here I can see that when it goes from MB3 from B1 is going to be equal to when I go from B2 to B3 times B2, B1. See how that's related? So here is this linear transformation, and then it's all going, the output is with respect to B2, but instead I have the information where it's going with respect to B3. So inherently the change that's going to be made is the change of basis matrix P, B2 to B3. They want us to solve for that. Like out of space, but I can write this out where I have 5, 3, 1, 1 is my output, and then I'm solving for P, B3 from B2 times 1, 2, 3, 4. So to solve for this, I can take the right hand, one more space, so we can go to the third page. Just rewrite this. 5, 3, 1, 1, P, B3 from B2 times 1, 2, 3, 4. I want to isolate this, so I'm going to multiply this guy by its inverse on the right. So 1, 2, 3, 4 inverse. Therefore, on this side, I also need to multiply it on the right. Like if I were to do this and then go 1, 2, 3, 4, -1, that's wrong. This is not an equation. This is not equal. I have to make sure to do it on the right-hand side of this matrix. 2, 3, 4, -1. So these are going to cancel out, leaving me with the fact that the matrix of interest is this, where the inverse of this, I did not solve for it on here, ends up being -17/2, 9/2, -9/2, and a 5/2. And that is the change of basis matrix that goes from B2 to B3. One more change of basis example, as I think really just to nail down the concept of change of basis. So this one's actually from the 4.2 prep quiz. It's the exact same problem. So if you are also doing the prep quiz, this is the answer. Okay, so we have the standard basis as we normally do, and we have a basis B. So B is 2, 1, 3, 2. This is kind of getting us, because all the previous examples have been about the change of basis matrix, but here I want you to really understand what the idea of change of basis is. So question is, if 5, 0 with respect to S is equal to AB with respect to B, what are A and B? So they're saying if I have a vector 5, 0, that is 5, 0 with respect to the standard basis, what is that vector with respect to the B basis? So 5, 0 with respect to S tells us that it's 5 times the first basis element times 0 times the second basis element. That makes sense, obviously. But now we want to know what is it when we combine with my other basis, my B basis. So this is asking us, how can I make 5, 0 using my basis element? So 2, 1 plus B times 3, 2. That's what it's asking us. If you can tell, we already also have, based on what we're talking about, the change of basis matrix that goes from B to S just by going like this. Cool. So to solve this, to solve for the coefficients that I use to linearly combine with my basis B to get 5, 0, I would end up doing this system, right? AB is equal to 5, 0. And then to solve for AB, I could take the inverse of this, 3, 2, -1, multiply it on the left on this side as well. 2, 1, 3, 2. And then this is going to give us, what is it with respect to B? Let's think about what it looks like with what we've talked about previously with the change of basis matrix. So I have my change of basis matrix that goes from B to S. However, I want to go from S to B. So I need the inverse of this, 2, 1, 3, 2, -1. Then I can take my input, which is my 5, 0 with respect to S, and that's going to give me something that in result is with respect to B. These are the same thing, solving it the same way. It's just using two different systems of logic. So it shows us that the change of basis works, change of basis matrices work, and like, what does it really mean? So in this case, we can just continue to solve it. So the inverse of this matrix ends up being 2, -3, -1, 2, that I then multiply by 5, 0 to get 10, -5. And that is it with respect to B. So in this case, A is equal to 10 and B is equal to -5. Now, going the other way, if I have something with respect to B already, and I want to go with respect to the standard basis, I just need to go the other way. So again, I already am given B to S. We know that already, so 2, 1, 3, 2. I have something in B, and I want to go to something in S, and I have something to get there. So my CD with respect to S, I can multiply by, write this out first, times something in B. You see how the B goes together here and then the S. It just makes sense. So CD S is equal to 2, 3, 1, 2 times 5, 0, which ends up being 10, 5. So C is 10 and D is 5. So think about it the same logically. That means that I have some vector that I linearly combine my basis elements with for B using 5 times the first basis element plus 0 times the second basis element. And that also gives me 10, 5, because here we're talking about with respect to the standard basis. So this is going to be what it is with respect to the standard basis, because this computation is just giving it to me with assuming the standard basis as the coordinates. Cool. Let's do a quick rank nullity theorem example. So the rank nullity theorem, like we discussed, so this is just asking us to understand how they're all related. So find the basis for the row space, column space, and null space of the matrix. So the first step to doing any of these is always to solve for the reducer echelon form. Unfortunately, you're going to be doing a lot of reducer echelon form solving in this class. So skipping that step exactly, so just solving for the reducer echelon form, I get this to be it. So looking at it, I can see that I have I have 3 pivot variables. I have 3 non-zero rows. I have 3 pivot variables in my columns. So the basis of my row space is going to have 3 things in it. The basis of my column space is going to have 3 things in it. And my rank is 3. So the basis of the row space, I can just take the non-zero rows in the reducer echelon form. So in this case, it's just every single row. So 1, 0, 0, 1 third, 1 third, 1, 0, 1, 0, 1, 0, 4 thirds, 7 thirds, 7 fourths. And then 0, 0, 1, 1 third, -2 thirds. When you're writing the basis for the row space, I wrote them as rows. I kept them like horizontal. You can write them vertically and that's still right. So writing them as columns isn't going to be wrong. For the basis of the column space, so my rows are just going to be my horizontal rows. My columns are going to correspond to the columns with pivot variables. So these are my 3 columns that have pivot variables, but I have to take the original columns. So these columns. So the basis for the column space is also going to have 3 things in it, but it's going to be the things from the original matrix. And that's the basis for the column space. So, different ideas. For the row space, you could also always go back and use the original rows as well, because when you're doing it, the row linearity relationship is preserved. Either way, up to you. Lastly, they want us to solve for the null space. So, if you remember, the way we solve for the null space is we take the reduced or echelon form and we augment it with the 0 vector. Looking at this, the first thing we do is figure out what is the equations that we're given. So x1, so I've got x1, x2, x3, x4, x5. x1 plus 1/3 x4 plus 1/3 x5 is equal to 0. x2 plus 4/3 x4 plus 7/4 x5 is equal to 0. I think it's supposed to be 7/3 instead of 7/4, but oh well, that's not what I'm talking about. x3 plus 1/3 x4 plus -2/3 x5 is equal to 0. So I have the expressions. I want to get all of these where my pivot variables are by themselves in terms of the free variables. So -3 x to the 4 minus 1/3 x to the 5th. x2 is equal to -4/3 x to the 4 minus 7/4 x to the 5th. x3 is equal to -1/3 x to the 4th plus 2/3 x to the 5th. Now that I have this, I can form my skeleton. So I've got x1, x2, x3, x4, x5. I know that I need to have a column for every single free variable. In this case, I only have 2 free variables. My free variables are x4 and x5 because they don't have a pivot variable in them. So I need a column for x4, and I need a column for x5, and then I can fill in from there. So this first expression, x1, is equal to -1/3 x4, -1/3 x5. x2 is equal to -4/3 x4 minus -7/4 x5. x3 is equal to -1/3 x4 plus 2/3 x5. And then remember that x4 is going to be equal to itself, and that x5 is going to be equal to itself. And then that is the basis for your null space. So you can write it like this, or you can write it in this like set notation where you get rid of the addition terms and then you just add a comma with the curly brackets. So that is the basis for the null space of this matrix. They want us to, I guess I didn't write it in the question, but note that the rank, so the rank tells us how many things are on the basis of the row space or the column space, is 3. The nullity of A is 2 because there's 2 things here. The rank plus the nullity, 3 plus 2, is 5, which is the number of columns that we had in the original matrix. That's rank nullity in action. Cool. Okay, let's do our worksheet questions and then we'll be done. There are only 2. Change of basis. Another change of basis question. So we have, now we're talking about in the polynomial spaces, so it's going to be slightly different than the idea of vectors, which will be good practice. Recall that P3 is the vector space of polynomials up to or equal to degree 3. We've talked about this before. Let W be a subspace of P3, consisting of polynomials that satisfy P of 1 is equal to 0 and P of -1 is equal to 0. So there is always all of the polynomials up to degree 3, but that obey the property of P of 1 equal to 0 and P of -1 is equal to 0. They're telling us that W is a subspace. We don't have to prove it, which is great. So they're like, believe that this is a vector space. One basis of this subspace is B1, which is these 2 things. Another basis is B2 with these things in it. So they're telling us these are 2 different bases for P, for this W. What is the polynomial denoted 2, 3, B1? So we have this polynomial 2, 3 that we can write as this, it's called the coordinate vector, because it tells us like what we use with our coordinates, essentially. So it's just saying what is the polynomial where it can be referenced, it can be written as 2, 3 with respect to B1. So we just need to figure out what we multiply our basis elements B1 by to get this. So this would just mean I would do 2 times 1 minus x squared plus 3 times x minus x cubed, which will give me 2 minus x squared. Oh, 2, I'm really bad at distributing. 2x squared plus 3x minus 3x squared, x cubed. That is our first polynomial. Then, question B, what is the polynomial generated 2, 3 with B2? So they're saying, I have 2, 3, this time with respect to B2, what is that going to look like? Same idea, we're going to use our basis elements and write what that ends up being. 2x squared is this. So 2 minus 2x minus 2x squared plus 2x cubed plus 6 plus 3x minus 6x squared minus 3x cubed. So we can combine these a little bit and get negative x cubed. That gets rid of these guys. Negative 8x squared. Yes. Just making sure I didn't mess up distributing anywhere. Plus x plus 8. Great, I did that right. Cool. So we did that. We did A and B where we said what is the polynomial with these two different coordinate vectors. Now they want us to express the polynomials in the basis B2 in terms of the basis B1. So they're telling us we have our polynomials in the basis B2. What do we need to do from the elements in B1 to get them to be the elements in B2? So looking at each of my basis elements, the first one is 1 minus x squared plus x cubed. How can I linearly combine the elements in B1 to get that? So what C1, I guess I'll just use C1, I don't know. C1 times 1 minus x squared plus C2 x minus x cubed. How can I make that happen? Same thing for B2, so, or the second element in the basis 2 plus x minus 2x squared minus x cubed. I'll call it D1, or I'll do C3. C3, 1 minus x squared plus C4 x minus x cubed. So this is what they're asking us. How can we express the polynomials in the basis B2 in terms of the basis B1? So how can we solve for this? This one is pretty easy, this first one, because if you can see just visually, you could solve this out. Like you could do the solving the system and figuring out what it is, but looking at this, I know I just need this to be a 1, and I know that I need this to be a negative 1. So the first element with respect to B1 is 1, negative 1, B1, and that's how we could write that as the coordinate vector. And then same thing for the second expression, looking at it just visually, I can see that I need this to be a 2, and I need this to just be a 1. So then this one can be written as 2, 1, B1. And that's what they are with respect to B1, the basis elements in B2. And then this leads us to what is the change of basis matrix that goes from B1 to B2. So how can we get something from B1 to B2? Here, we went from B2 to B1. So we generated, using that solving before, we generated what the change of basis matrix is going from B2 to B1, which is just 1, negative 1, 2, 1. And instead, if we want to solve for the change of basis matrix going from B1 to B2, I'm just going to take the inverse of this. Equal to change of basis B1 to B2, which ends up being 1/3, negative 2/3, 1/3, 1/3. And that's that. So not too bad. Change of basis, using polynomials this time. We didn't even have to solve for the basis. They gave us the basis, which was nice. I was worried we're going to have to solve for the basis. So not too bad. Rank nullity theorem question, very similar to the one we just did before. Pretty much we need to solve the reduced rational form of each of these. This is already the reduced rational form, so let's do this one first, where we want to find the dimension, the bases of the row space, column space, and null space. So I'm going to do row space, column space. I have enough room to do that. bad. Row space, column space, null space. I'm gonna do this with A first, because again, A, this is equal to the reduced row echelon form of A, just looking at it. The base of the row space is each of the rows. And this time I'm going to write them as columns for my own sake. So 1, 0, 0, 0, 0, 1, 0, 0. The rank is obviously 2. Basis of the column space, again, we look at the non-zero row, the non-zero columns, and we go back to the original matrix. Here they're both the same, so then I can just write them as 1, 0, 0, 0, 1, 0. The rank here is also 2. And the basis for the null space, these two guys. Basis for the null space, I'm going to solve for it real quick. Cheating using the rank nullity theorem, I know I'm looking for 2 things because the rank is 2, so the nullity must be 2. Here this tells us that x1 is equal to 0, x2 is also equal to 0. We know that we have 4 variables to solve for, so I'm going to make the skeleton. I have 2 free variables. I have x3 and I have x4 because there is no leading one in either of those columns. Those are free variables. Here, this also confuses a lot of people on how to solve for the basis of the null space of this, but essentially you're just saying what is obviously true. So they're telling us x1 and x2 will always equivocally be 0. So you can just put zeros here, and that x3 is equal to itself, and that x4 is equal to itself. So it's just like that. And that's the basis for the null space, which means it also has a nullity of 2. Quick and easy. And then let me just move this down. Just keep that. The row space for B. So I need to do the reduced row echelon form of B because it's not already in the reduced row echelon form. So imagine we solve for the reduced row echelon form, but instead I'm going to cheat. Where I have, okay, 1, 0, 0, 2. I'm looking at the answer key. I should have done this on my own. Where they're saying this is an echelon form because we have the first leading ones in each thing, and this tells us enough that we need to know, which is true. I always prefer to do it to reduce row echelon form, but whatever. So starting off, the row space is going to be our non-zero rows. So in this case, we have 3 pivot variables. So we're going to have 3 basis things. Oh, I used the wrong color. 3 things in our row space. So 1, 2, 3, 0, 1, 1, and 0, 0, 1. Because like I said, the basis of the row space doesn't have to be the reduced row echelon form. It can be the original rows, or it can be in this echelon form, because the span of the rows does not change with row operations. Up to you. The column space, again, is our non-zero columns. In this case, all 3 columns have pivot variables in them, but remember, we have to go back and use the original rows. So the basis of my column space here is 2, 3, 4, 1, 2, 2, 1, 4, 2, 0, and 0, 1, 1, 3, 2. So here, rank is 2. Same thing here, we have 3 things in there, rank is 2. Now, null space. Oh, rank 2, rank 3. I can't count. The basis for the null space is going to have a nullity where rank plus nullity is equal to the number of columns. However, the rank was 3. There's 3 columns. That means the nullity is 0. That means the basis for the null space is just the trivial solution. And that's it. Oh, sorry, this is the wrong size of this. The null space is, you can write that it's just the trivial solution, that it's empty, that it's 0. All of these things are the same. The size of the, sorry, I had to fix this because the size of the null space and the size of the row space are the same, because the null space is defined for every variable, and here we only have 3 variables. But yeah, this will save you time using the rank nullity theorem, because you're like, I know that the null space is empty because the rank is 3 and there's 3 columns. it makes sense that we only have pivot variables. We don't have free variables. There's nothing that's going to correspond to the null space. Nothing's going to generate the null space. So yeah, that is 4.2. So it's a bit of change of basis, a more complicated topic that is going to require some practice, and then rank nullity theorem and the idea of row spaces, column spaces, and null spaces, which are, I think, really cool and not that challenging and just important to know in the future. But yeah, that's 4.2.